Okay, well, it's such a pleasure being here. Thank you, Ray and Ivan, for inviting me. It's a very interesting meeting and already a lot of good material presented. So again, thank you to the organizers, NSF, of course, and in particular, Ray and Ivan and everybody else in the organization. I know it takes a lot of work. I apologize because I just discovered that if I go into presentation mode, somehow my PowerPoint crashes. So please bear with me. You get to pick ahead of me, which is unfair, but that's okay. Lose a little bit of a punchline effect, but it's best I can do. So I don't know if you can see my, on the side I have the pictorials. I'm gonna minimize that, okay. All right, so this talk very much it follows close to what you did before last, Michael, on the understanding the performance you can expect of mmWave. So as you know, you heard me before, there was a lot of discussion, skepticism, and at some point it was thought valuable to provide some real industrial grade, tier 1, telecom grade, industrial strength, whatever you want to call it, data, hard data, so we can do 90% coverage with statistical significance. Out of necessity, this report talks about collecting such data in the urban canyons, Manhattan. And I need to take the time to acknowledge our collaborators, which is a big set of people. I'm just setting up here my timer for 20 minutes. And we in particular, Gil Zussman and his team in Colombia, and Rodolfo Fake and his team in Chile. And a lot of effort goes into this type of activities, as you probably appreciate. So if you just want to take the 2-minute summary and go check your email, this is your executive slide. So if you want to do reliable 90% coverage at 28 gigahertz in urban canyons, you need to develop sufficient amass sufficient database to do that with statistical significance. And so we collected 20-something million individual power measurements in 3,000 links in 2 different cities in 12 different streets. The bottom line is that under reasonable assumptions listed here, you can actually deliver, just like Michael found, rates up to 350 megabits per second with intersite distances of 400 meters, so out to 200 meters, pretty much consistent with what was mentioned before. I highlight they are outdoor because these measurements were all from rooftop to the pavement. And as you can imagine, we all know by now 80% of data traffic is actually inside dwellings. And there is a huge uncertainty on building penetration loss. But it's always good to leave some activities for future work, right? So put it into that category. But at least the news up to and at the outside of the building are encouraging. And so also we found that angular spread does not take away a lot of the antenna gain. It's something to consider, but it's a minor 2 dB effect. So we can indeed take advantage at least of the antenna gains that we use here for the 20 so dBi. We'll get into that. And what we found very interesting is that streets are actually canyons. They are canyons, and the beam is wide compared to the street geometry. So you only need to point the antenna up street, down street, east or west, and you're done. And you know, elaborate pencil beam pointing ideas are more in the figment of imagination because they bring very little additional loss to compare to this very simple, inexpensive fixed pointing. So let's get into details. So in order to measure this, of course, very quickly we learned that tier 1 service providers are very cost sensitive. It would be easy to do hyper densification for ultra wideband. Rates would be fantastic, expensive, and impractical for all sorts of reasons we've discussed before, to do with the municipal permits, getting power, getting backhaul, et cetera, et cetera, et cetera. So the first question is, or perhaps the only question is, what can you achieve from existing sites? So existing sites are either at the edge of a roof or on the roof, or maybe with some set off from the roof because of sometimes there are municipal rules that force you to maintain a certain aesthetic coherence or safety, whatever. But the variables are either on the roof itself or with back off. So the base station emulation is on the roof. That's where we are more interested in finding their activity. So we have our rotating scanner that allow us to record at a fast speed, 300 revolutions per minute, record a full 360 degrees of power angular spread. So for that, so for critical items that we need to address before we can do this 90% coverage, of course, it's link budget. And the three ingredients that are paramount are path loss, how much direction gain can we actually get, and angular dynamics. So path loss, we need to have a lot of measurements to nail that because there's a lot of statistical variability. And we wanted to get out to 800 meters with reliable measurements. And angular dynamics is covered by what I said before, the rotating scanner. So we built a portable CW, continuous wave, very narrow band. So I think it's 20 kilohertz. So we have enough power to go down to 170 dB of path loss. So that's very generous compared to operating equipment that the kind of bandwidth that you would do. And so give us extra room to get this reliable 10 dB measurements almost everywhere we go that we want to, while staying on the pavement, I should emphasize. And certainly not around corners. We'll do some of that, we'll discuss, but shy around the corners, I should say. So we have the rotational antenna, 24 dBi in the turntable at 300 revolutions per minute for angular dynamics. So this is a sampling of Manhattan. This, I think, is particularly relating to collaboration with Columbia Fellows. And on the right-hand side, you see a picture of one of their balconies, which is a nice sort of roof edge location. And that's where the rotating scanner in the red circle, the receiver is. And then on the left, you see the typical, we would displace the transmitter emulating a user up and down either same side or opposite side in the street. As I said, 12 streets, 7 different buildings, 2 cities, Manhattan and Valparaiso, Chile, building up significant database. So here is the data. So you want to look at data. A lot of things come to mind from this chart. So these are all measurements in the places that are typical of what you saw before. These are all at roof edge, same street, and in the pavement, no into the building penetration. And what is interesting is that if you wanted to fit a standard 3GBP, you actually have 2 choices. You could pick line of sight or non-line of sight. Well, in terms of line of sight, it's very close to free space, and it's too optimistic. And you see on the faded gray on the graph where it says 3GBP UMA LOS. And almost all the points are below that, certainly beyond, say, 100 meters. And then on the other extreme, you have the dash black at the bottom where it says 3GBP UMA non-line of sight. I don't know if you can see my cursor, but I'll use it anyway for myself. And that's way too pessimistic. So that you don't want to do this. If you're too optimistic, your user is going to be very unhappy. If you're too pessimistic, then your business case is going to be hurting because you're going to have to, you will be demanding super hyper density. So our data, once we do the fit, then with a 2 parameter fit slope and intercept, we end up with a slope of 3.5, 3.6, and an offset of 35 dB, and which is 11 dB more than free space. Now notice that this rooftop to same street. So is it line of sight? Is it non-line of sight? Well, we actually learned to stay away from that a priori characterization, which we want to impose on the data. But I think there's much more going on, whether it's foliage or street furniture, et cetera, et cetera. And you see that very clearly in the next picture. So what you saw before in different colors on the cloud, you see here CDFs. So each CDF represents one street. And you know, if the range, it's very wide, it's 30 dB. On the left pictures, you see a street with typical Manhattan street canyon, but essentially no vegetation. On the bottom left, you see a slightly more residential neighborhood, narrow street. The top one may be an avenue, yeah, it's 7th Avenue. The bottom one is a street, and there is more foliage. What exactly is going on, it's hard to tell, but it's one dramatic observation is how wide the variance is on street to street. So you see it here in the cloud itself. It's a lot of spread. The feed is nice. It, you know, it has an RMS error of the feed is 7 dB, which is not that different from what people used to do in the Hatta models world, but that's where statistical over many city blocks. This we are in the same street from rooftop, and yet there is still a lot of variability, as again characterized there. From the rotation, we do power versus azimuth, as in the top right, and from there we can compute the gain that is actually realized in the presence of scattering. And the good news is that the left graph shows the angular spread CDF. So you see that 90%, we're talking about less than 7 degrees in the lamppost or roof edge, and in the black, a little more when the base station or emulator is hidden behind the edge of the roof. So you see now the angular spread going up to 12 degrees. But either of them are not too dramatic in terms of, you know, obviously, you know, would you do a convolution between the actual nominal antenna radiation pattern as you would be measuring free space with the power angular spread of the channel to obtain the actual, you know, coupled channel effective directivity. And when you do that, you can never be narrower than the channel itself. So you know that you're never going to be able to create a beam narrower than 12 degrees, say, in the rooftop setback. And you can compute from there a gain, effective gain degradation. So then you see that is 90% of time this degradation is less than 2 dB for the lamppost and roof edge positionings, but it can be up to 4 dB in the roof setback. Now, these numbers are certainly not negligible and important to keep in mind, but certainly they pale in comparison with the uncertainty of penetration into building due to material loss variability. Variability from street to street, we just said is 30 dB. And of course, the obvious one, if you are comparing to deployments, and we should, just like Michael did, compare to low band, because as I said, tier 1 service providers for business reasons want to use the same side grid. So when you do that, you're going to have the F1, F2 squared, which is another 30 dB. So in comparison to those, these are smaller factors, but still important. Now, what about this pencil beam, laser, dynamic pointing? If the stop sign pole blocks me, I'm going to pick another direction. Well, it turns out that you basically have two directions: straight line of sight down or straight shortest path down the street, or you bounced off the opposite wall. And you can see here where we unpack the angles. You see the graph on the left. So you either are in line of sight with the blue approximation, and you see the actual measured angles are nicely fitting that. Or in the bottom, you have the building reflection geometry in the smooth red curve, and the measurements past 100 meters, you start getting a significant reflection, say within 5 dB of the main one. So interestingly enough, if you knew this after the fact and you just took long-term average of directions and just point there and keep it fixed, then you get on the right-hand side chart, you get on red, best average direction. On the other hand, if you were a genie told you on a per turn basis what is the best direction, and you pointed there, all improvement you get is the blue, which is almost identical the same. And actually, quantitatively speaking, you are within 3 dB. So doing a lot of sophisticated beam pointing would be for very little gain, at least as the measured data shows. Now, the other big important question, of course, is around the corner. And we developed a very nice model. You see how it So let me take you to how the measurements were done on the right-hand side chart. So red would be line of sight to the base station situation. And then when you face the first corner, that would be on the blue. The antenna on the pavement would just walk around 90 degrees and go deeper and deeper into the corner, as you see on the left-hand side with the blue circles. Or alternative measurement, continue on the red trajectory and then make a left onto the yellow trajectory. And then you have the graph of propagation losses in the middle, and similarly with the green. We've developed a diffraction-inspired model that fits the data very well. You can see how measurements and models are on top of each other very clearly for the yellow and green turnings. And in the purple, it gives us confidence that while we didn't measure the curvy part at the bottom, the other ones seem to follow that very well. So you get the red circles on top when you are on the same street, and then you get the turnaround. From this, we can estimate what's going on with our link budget. And you get a 14 dB drop after 10 meters, and then 20 dB drop after 50 meters into the corner. So non-negligible, 10 to 20 dB. But a lot of the distances, when you are in same site outdoors, same street outdoors, there is plenty of signal. So maybe some level of around the corner is possible. Inspired by that, we did a high-level simulation where we show a Manhattan-like city, but this is all, of course, a synthetic, abstract, and then consistent with the avenue separation and street separation. And we place antennas at 400 meters ISD, which again is typical of what you would find in commercial deployments. And the good news is, yes, confirming what was discussed before. You can deliver rates of something like 350 megabits per second to 90% of the locations or more. And of course, you would use for that 800 megahertz of bandwidth at 28 gigahertz, transmitting 20 dBm with a 33 dBi antenna gain. And in the UE, you would have a typical noise floor of 9 dB with a 6 dBi antenna gain, which is mild. You don't want to push UE antenna gain too much because you have problems with aiming that antenna and blockage by, we haven't said anything yet about going into rooms and whether you're aiming to the window or you're covering the terminal with your head or not. So we were trying to be shy a little bit on the UE gain here for those reasons. But all in all, if there is a good interest, high interest in street coverage, the news are good. And the spectrum is plentiful. Using 800 megahertz to deliver several hundreds of megabits per second sounds good. Now, in summary, what I just said, this is again 300 megabits per second that we are confident 90% with statistical significance with parameters just mentioned. Directional antennas at the base are highly effective because the angular spread is narrow, at least for the directivities that I discussed. And precise beam pointing does not seem to be needed in this case. You really ought to think of 4 panels, maybe at the intersections, or 2 panels at the middle of the street. And we are able to make these statements based on a very, very massive data set in 3,000 links. Important to note that this gives us significant more accuracy and relevance to tough business decisions because 3GPP was either too optimistic or too pessimistic. But it's important to know the 30 dB street variability. So, there is a challenge here. Either we have to have enough link budget to live with it, which we've done in this calculation, or we need to have some further smarts on how to adapt to site-specific conditions. Again, excess loss around the corner is not the end of the well. You probably certainly seems to be able to go at least some tens of meters. And we've developed models that are quite accurate for this type of situations that we've exercised to do these predictions. And I think with that, I would rather save the remaining time to answer questions. Oh, I should also say the best angle over time is very stable, and long-term average point up the street, down the street seems to work quite well. And again, there is no dramatic gain loss from scattering, even when the antenna is set back from the roof edge. 4 dB is kind of the list of the important attenuation factors playing into this link budget that clearly from the beginning at mmWave was one of the most challenging issues. So thank you very much for listening to the talk and to the organizers, and I'll be happy to answer any questions.
Thank you, Reinaldo. So we have time for a couple of questions. So let's look in the questions posted. So I don't see anything here yet.
I actually have a question, Reinaldo. So what do you think would be the impact of say, pushing the channel to 800 megahertz at 28 gigahertz, or even higher at 60, if you go to these extreme bandwidths? What do you believe that we can just extrapolate the channel model for narrowband data collected, or do we need to do wideband measurement?
Oh, that's a very good question. So wideband measurement. So it's always nice to have the data, but nothing that we observed tell us that we should be afraid of something that's surprising or out of the ordinary. So previous measurement campaigns have characterized delay spread quite well. So we know what the delay spread is, we know what the coherence bandwidth is. And I think it's as long as you understand that you're going to have, Rayleigh fading across bands that are beyond the coherence bandwidth, then OFDM can certainly even harvest that for diversity across frequencies. So no, I don't see any great difficulty beyond what's already been done or trial for sure with carrier aggregation, where you operate in very wide bandwidths.
Thanks.
Okay. Thank you again, Reinaldo.
There is one more question. What is the beam width of the fixed beam at the base station for azimuth and elevation?
Okay. All right. So beam widths. 10-degree horn, 24 dBi. And I think it was, if not square, it was close to square. So the 10 degrees is pretty much the same vertical and elevation and azimuth. You can see the antenna here on the top right, not quite. But it's of course, a small horn. Yeah, you can just about see it above the railing. But it's behind the ground plane. So, but you do see the dimensions of the mouth of the. So it is a little bit rectangular. So it has a little more gain in azimuth. So the 10-degree horn, I believe this 10 degrees azimuth. I need to get back to you on the elevation. 24 dBi, of course, is combined elevation and azimuth